everyone. I am Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. In my last video, band theory of solids, I have discussed about different electron theories of solids. So in that we have discussed about three stages of electron theory of solids, and mainly this electron theory of solids, they'll explain the electrical behavior of solids. Based on these electronic structure, how different properties of solids are going to change. So first came classical theory, and because of some of its drawbacks, then came our quantum theory. Even quantum theory also has some drawbacks. So all these theories, they can explain about the conduction in metals, and they can explain about thermal and electrical conductivity. But when we talk about why some solids, they'll behave as insulators, also as semiconductors, so they failed. So that's why next came our band theory of solids. And main thing is, what is the main drawback in the case of classical and quantum theory? In classical and quantum theory, what we have observed here is, in both the cases, he has neglected the interaction between the positive ion cores and free electrons. He has not taken into consideration interaction between positive ion cores and electrons. So what we have seen that, if we take any atom, in that atom, if we consider a solid, what we have seen in that solid consists of cluster of positive ions, and we have our conduction electrons moving freely inside the crystal. Okay, so here when classical and quantum theory is taken, they have not taken into consideration electrostatic interaction between this positive ion core and the free electrons. That's why they could not explain certain behavior of solids. But coming to band theory or zone theory, here that electrostatic interaction between positive ions and free or valence electrons, it was taken into consideration. So we are going to, and we have seen in our previous video that if we take into consideration such interaction, what we have observed here is, depending upon position of electron between the two positive ions, it is going to develop some potential. Okay, so and that potential, it is going to play very important role. So in our future sessions, we are going to see how that potential is going to change properties of different solids. So continuing with our session. Now, this is the famous theory, and of course, this is also called as band theory of solids, Kronig-Penney model, or it is also called as band theory of solids. So this band theory of solids, it was proposed by Kronig and Penney, two scientists. That's why it is called as Kronig-Penney model. So here we are going to see what is this concept of periodic potential and how this periodic potential is going to affect different properties of solids. So now, as we have discussed in our previous session, electron in a periodic potential, also we have discussed about Bloch's theorem. What is Bloch's theorem? When we have electron moving in a periodic potential, then wave function associated with such particular electron, it is given by one certain representation. What is that representation? Psi of x is equal to e to the power of ikx into ukx. So as we have seen that e to the power of ikx, it is a plane wave equation, and whereas ukx, it is called as modulating function, and it is also called a periodic function which has got same periodicity as potential of electrons. So this is given by our Bloch. So this is called as Bloch's theorem. Okay, now what is Kronig-Penney model? As I told you in band theory of solids, so if you take any solid, so what we have done here is how that solid is given. We have our positive ions. So again, I am taking positive ions along one particular direction. Let that direction be S direction. Now I have my electron moving, and I am taking how its potential is going to change. And when our electron is exactly in the middle, potential is maximum. I think we have seen this type of variation when we have discussed electron in a periodic potential in our last video. So when electron is exactly middle between two adjacent positive ions, potential is maximum. And when electron is approaching the positive ion, what is happening to potential? Potential is dropping to 0. And this variation of potential with position of electron between two positive ions, it is same for every two adjacent positive ions separated by A. What is our A? A is interionic spacing. So A, it is called as interionic spacing. So depending upon the A, potential is going to change. So this potential, it is called as periodic potential. Okay. So here, and I think we have written that V of X is equal to V of X plus A. So what is the periodicity of that potential A, which is nothing but interionic spacing. So the same concept here we are going to explain using this model. Now here, what you have, I have here, as you can see, we have our positive ions here. These are positive ions. I have taken one-dimensional crystal lattice. We have our positive ions. Okay, regular arrangement of positive ions along X direction because we have considered one-dimensional periodic lattice. Okay, and as I told you, when electron is exactly when it is middle between two adjacent positive ions, its potential is maximum. What is that maximum potential? In this case, we are taking it to be V0. V0 is our maximum potential. So this value we are taking it to be V0. So potential when your electron is exactly in between two positive ions, it is taken to be V0. Okay, so now when the same electron is approaching a positive ion, what happens to potential? Potential is dropping to 0. So what is happening to potential? Slowly it is moving towards the 0 value. So slowly it is dropping to 0. And it will be same for every two adjacent positive ions separated by A. A, it is called as interionic spacing. And when we take such periodic potential, when we take such variation of periodic potential, what is that variation of periodic potential? When electron is exactly at the center between two adjacent positive ions, potential is maximum, which is V0. And when electron is approaching the positive ion, its potential is dropping to 0. We end up having what we have now. If you see this figure carefully, see here, these are called as potential wells. So these are our potential wells or potential boxes. These are called as potential wells or potential boxes. And these are all potential wells or potential boxes. And whereas this are called as potential barriers. These are called as potential barriers. So when we take such periodic potential, we end up having potential wells separated by potential barriers. Okay. And what is the width of potential well? This potential well width is A, which is nothing but our interionic spacing. So what is the width of potential well? A. And what is the width of the potential barrier? B. Now here we are coming across two things. One is A and one is B. What is A? A is interionic spacing. So we have rectangular wells of width A. They are separated by potential barriers. So these are our potential barriers whose width is B. So there are two regions here. First region, what is that first region? We have potential well whose width is A. And these are separated by potential barriers. And what is the height of the barrier? V0. And what is the width of the barrier? B. And because we are taking here to be the origin, we will consider this other side width of the barrier to be minus B. So there are two regions. One is when electron is near the positive ion. What is that reason? 0 less than X less than A. So in that case, our potential is 0. Whereas we have second region, this is our first region. Here we have our second region when our electron is in the region minus B less than X less than 0. So what is the potential of electron? Potential of electron is V0. So how we are going to define potential function? So here potential function, it is defined in two regions. So it is 0 when our electron is in the region 0 less than X less than A. That is when it is inside the potential well of width A. A is interionic spacing and its potential is V0 when our electron is near the when it is at the center of two adjacent positive ions, or when it is in the potential barrier region, that is minus B less than X less than 0. So there are two regions. So when we consider such periodic potential variation, we end up having potential wells. And what is the potential of electron inside the well? V, usually it is constant, it is taken to be 0. And when your electron is near this potential barrier, its potential is maximum and it is given by V naught. So we have potential boxes separated by potential barriers. And in further slides, we are going to discuss in detail what is the role played by these potential barriers. These potential barriers, they are going to make an electron free or bound. So a free electron, bound electron concept. Why in certain metals they are behaving as insulators? Why? Because they don't have any free electrons. They have bound electrons. Okay, whereas in some solids, if you take, they are good conductors. Why? Because they have free electrons, and that completely depend upon this potential barrier strength. So in terms of this potential barrier strength, how the properties of solids are going to vary, that we are going to discuss in our future slides. Okay, now in order to further understand this concept of periodic potential to band theory, how bands have originated, what I'm doing, we have our Schrodinger's wave equation. So for a particle moving, we know that it will behave as a wave, and such wave motion, it is described by Schrodinger's wave equation. And what is our Schrodinger's wave equation? Schrodinger's wave equation is d square psi by dx square plus 2m by h cross square. Actually, that should be h cross square. H cross square E minus V psi is equal to 0. This is our Schrodinger's wave equation. So this is our Schrodinger's wave equation. So now I'm going to apply those two regions. What are those two regions? One, when your electron is inside the potential box or potential well. Okay. And in case of potential well, V is equal to 0. And this is our, whereas this region, this particular region is our potential barrier. And when our electron is near this potential barrier, what is its potential? Its potential is V naught. So when I'm applying those two regions to my Schrodinger's wave equation, I end up having two equations. What are those two equations? If I take V to be 0, I'll get this equation. Whereas if I substitute V is equal to V naught for this region, I'll get this equation. So these are the two equations. Okay, once we apply those two different regions, then we end up having two different Schrodinger's wave equation. Okay, and now I'm introducing two parameters in order to simplify those Schrodinger's wave equation. One is alpha square, and what is alpha square? 2me by h cross square. So it is given by 2me by h cross square. And what is our beta square? Beta square, it is given by 2m by h cross square into v naught minus e. What is h cross? H cross is equal to h by 2 pi. Okay, it is given by h by 2. So two parameters I have defined. One is alpha square, another one is beta square. So they are defined like this. Now I am going to make these substitutions in the Schrodinger's wave equation. Then I'll have my equations like this. So what is my alpha square? Alpha square is 2me by h cross square. So I'll have my Schrodinger's wave equation as d square psi by dx square plus alpha square psi is equal to 0. This is for the region when electron is in the potential well, where potential is 0. And here I'll get this equation. Why minus? Because we are defining beta square as V naught minus E. But here we have E minus V naught. So that's why here we'll have minus beta square minus beta square psi is equal to 0 when electron is near the potential barrier where potential is V naught. Okay. So these are the second order differential equations. And what is the solution generally for second order differential equations? It is given by psi of x. And now comes our Bloch's theorem. What is our Bloch's theorem? When we have electron moving in a periodic potential, wave function associated with such electron moving in a periodic potential, one representation is given. What is that representation? Formula is given e to the power of ikx into u of x. So if I consider solutions and if I simplify these two equations, okay, then I end up having one very important condition. Okay, so when we apply this solution using Bloch's theorem to this second order differential equations, if I try to simplify, we end up having this equation 4, very important equation 4. Okay, and if you carefully see this equation, we have here P. What is P? P it is given as, P is generally, P is equal to mv0 AB by h cross square. So it is given by h cross square. mv0 AB by h cross square. And of course, m is our mass, v0 potential barrier height, A is width of our potential box or distance between two adjacent positive ions, B is width of our potential barrier, and h cross is equal to h by 2 pi. So v0 is our barrier strength. So P it is given. Sin alpha A by alpha A, we know alpha. What is alpha? Alpha square, it is defined as 2me by h cross square, plus cos alpha A is equal to cos k. And what is our k? K is wave number or propagation vector. And this equation is very important in order to understand the concept of band theory. So what we have done, we have taken Schrodinger's wave equation, we have applied it to two regions, and those regions were formed because of periodic potential. We end up having two more modified second order differential equations. Then we have taken help of Bloch's theorem, which will give solution for those second order differential equations. Then we end up having this very important condition given by equation 4, and this P. So actually it is scattering power of, this is called as scattering power of potential barrier, or it is also called as potential barrier strength, because here it has V0. V0 is height of the potential barrier. Okay, now we are going to see how this equation is going to help us for band theory. Now what I have done here is, so what was our equation? P sin alpha A by alpha A plus, okay, cos alpha A is equal to cos Ka. P sin alpha A by alpha A plus cos alpha A is equal to cos K. So this is the equation which we got. Now what I am going to do here is, I am going to plot a graph. So what I am going to do, on x-axis, I am going to take alpha A, okay, and then on y-axis, I am going to take this left-hand side of this equation. What is the left-hand side of this equation? P sin alpha A by alpha A plus cos alpha A. And what I am doing, this left hand side of this equation, I am taking P, I am fixing it to one particular value which is equal to 3 pi by 2. Okay, so if I take different values of alpha A, in this A is constant because A is, what we have here, I have alpha A. So here A is constant because it is inter-ionic spacing. Alpha is variable. Alpha is variable, and we usually will take multiples of pi. So we'll take pi, 2 pi, 3 pi and 4 pi and so on. So here we'll take minus pi, minus 2, multiples of pi will take for alpha. And for different values of pi, we have to consider these angles. If I substitute here taking P to be 3 pi by 2, what type of figure we'll get? Okay, so that way, so if I plot taking alpha A on x-axis and then taking left hand side of equation 4 on y-axis, then I end up having this particular figure. So we end up having this particular figure. Now how we got this figure? Now if you see here, this is our x-axis. Okay, on x-axis I am taking alpha A. A is constant and my alpha is variable. So it will be plus or minus pi, plus or minus 2 pi, plus or minus 3 pi. So here I'll have different values of alpha. So this is for pi, 2 pi and 3 pi, and this is minus pi, minus 2 pi and minus 3 pi. So we'll have positive and negative values. Now, what I have done here is I am limiting, okay, my y-axis or value of p sin alpha by alpha a plus cos alpha a between +1 and -1. I'm saying that this left hand side value, once I substitute values of alpha, okay, it should be between +1 and -1. Why is it so? Now see here, I have plotted now right hand side. What I have on right hand side of this equation, cos. Okay, so now coming back here, we have this equation. So this is our right hand side and this is our left hand side. So this is left hand side and this one is right hand side. And what we have on right hand side, cos, and we know that cos value, it will be between +1 and -1. Okay, and this RHS is equal to LHS. So this total value, it should also be limited between +1 and -1. So this total value, it should be limited between +1 and -1. Okay, and this I am fixing. P value is fixed. What is the value of P fixed? 3 pi by 2. So here I am substituting different values of alpha. Okay, now when you substitute different values of alpha, you will get different values of this left hand side. You'll get different values of left hand side. But which values are permissible? Values only that are between +1 and -1. I'll get different values of left hand side once I substitute different values of alpha. But I have to consider only those values of alpha. Here you take, I am saying permissible values of alpha. What do you mean by permissible values of alpha? These are those values of alpha. When I substitute those values of alpha in left hand side equation for p is equal to 3 pi by 2, your left hand side value, it should be between +1 and -1. It should not go beyond +1 and -1. Those values of alpha, it is called as permissible values of alpha, permitted values of alpha. So you can also say these are called as permitted values of alpha. These are called as permitted values of alpha. Okay, so what are those values of alpha? Values of alpha for which left hand side of this equation falls between +1 and -1. Why it has to be between +1 and -1? Because right hand side I have cos, and always cos, it is bounded between +1 and -1. What about the other values of alpha? Other values of alpha which I substitute here and which are making this LHS go beyond +1 and -1 values, they are called as unpermitted values of alpha. So here, after plotting this graph, I am getting permitted values of alpha and unpermitted values of alpha. What are permitted values of alpha? If I substitute those permitted values of alpha, left hand side of this equation, it will be between +1 and -1. It will be between +1 and -1. What are unpermitted values of alpha? For these values of alpha, what will happen? Our value of this left hand side, it will go beyond either +1 or -1. Now, if you see this regions, what are these regions? These shaded regions, I'm shading them. So what are these shaded regions? So this shaded regions, these are formed by permitted values of alpha. These are formed by permitted values of alpha. Okay, so here you will have different values of alpha. And if I substitute these values of alpha, my left hand side of this equation is falling between +1 and -1. After that, if you see these values of alpha, these are those values of alpha. If I substitute those alpha values in left hand side, it is going beyond either +1 or -1. Again, I formed one region, shaded region. Here also I have some set values of alpha, permitted values of alpha, for which my left hand side will be between +1 and -1. Again, followed by certain values of alpha, for which left hand side of your equation it goes beyond +1 and -1. Again, permitted values of alpha. So these shaded regions, these are formed by those values of alpha for which your left hand side it falls between +1 and -1. Whereas these unshaded regions are those values of alpha for which your left hand side is going beyond +1 and -1. So the shaded regions, they are called as permitted regions formed by permitted values of alpha. Unshaded regions, they are called as unpermitted values of alpha or forbidden regions. Now, what is our alpha? Alpha, it is given as alpha square is equal to 2me by h cross square. So when you're talking about from this, what is our E? E is alpha square h cross square by 2m. If I'm able to get permitted values of alpha, I'll be able to get permitted values of energies. It means that this is the allowed energy region which is formed by permitted values of alpha, and this unshaded region is forbidden region which is formed by unpermitted values of alpha. So these are allowed energy regions and these are unallowed energy regions. So these regions are nothing but your bands. This is allowed energy band. What is the difference between a band and level? Band, it is if you take your energy band, when we consider our energy band is made up of series, continuous energy levels. Okay. So here also I got energy levels. These are continuous energy levels. And allowed. Allowed means electron can move only with these energies. Why? Because +1 and -1. Because of this factor +1 and -1. So these shaded regions are allowed energy bands and these unshaded regions are forbidden energy bands. So this is the first important conclusion from this graph. So what is that conclusion? First conclusion is the energy spectrum consists of allowed energy bands and forbidden bands. So are you able to see this waveform here, which I have given? In this waveform, I am showing this waveform only in the shaded regions. It means that electron, it can move only in the allowed energy band. It is not moving in forbidden energy band. So this is the one important thing. So we came to know energy band concept. So how we got those energy bands? What are energy bands? Energy band is set of closely spaced energy levels. And this allowed energy band is formed by set of allowed energy levels. And how I got those energy levels? From permitted values of alpha. And from where I got these permitted values of alpha? What I have done, I have considered only those values of alpha for which left hand side of this equation is between +1 and -1. And how this forbidden energy region is formed? It is formed by set of unallowed, not allowed energy levels. What are not allowed energy levels? Which are formed by those values of alpha which are unpermitted, which are not permitted, not permissible. Why? Because if I substitute those values of alpha, left hand side of this equation, it will go beyond either +1 and -1. Okay, and second most important point what we have to consider here is, as alpha A is increasing, what is happening here? You will observe that width of allowed energy region is increasing, whereas width of forbidden energy region is decreasing. So these are the two important conclusions from the graph. First one is formation of energy bands. What is a band? Band is set of closely spaced energy levels. Here it is giving rise to allowed energy bands and forbidden energy bands. And second thing is, as alpha A increases, allowed energy band, what is happening? It is becoming broader, and whereas unallowed, so here broader allowed energy band, whereas narrower forbidden energy band. And one more thing what you will observe here is P. P is our potential barrier strength. I think we have seen in our figure. So we have potential barriers and our electron is here. Suppose our electron is in this box. Okay, whether this electron, it will be a free electron or whether it will be staying in that box, it depends upon the strength of P. What is P? P, it is given by mV0 AB by h cross square. So P depends upon V0. So if V0 is 0, So it will act as, if V naught is equal to 0, P is also 0, there are no potential barriers, so electron, it will be a free electron. So our electron, it will move freely. And our allowed band, it will be a quasi-continuous. Whereas, if this height is infinity, it means that our electron, it is not going to come out. So when V naught is infinity, then potential barrier strength is also infinity. So electron cannot come out of this potential well. So here, it is bound in that potential well, so you'll have line spectrum. So about this free electron and this bound electron having continuous allowed energy band, quasi-continuous energy band, and having line spectrum, that we are going to discuss in our next session. Okay, so here we have discussed about our different allowed energy bands, forbidden energy bands, and here we have seen that depending upon the potential barrier strength P, your electron, it is behaving as a free electron or bound electron, whether you have quasi-continuous allowed energy band or whether you are going to have line energy level or line spectrum. So that we have seen from this Kronig-Penney model. Okay, so thank you. I'm going to end my session here.
Like, share and subscribe. Hit the bell icon for more updates.